Alrighty guys, so tonight we are going to be talking about electron configuration. So electrons can be described by 4 quantum numbers like you guys learned about. These quantum numbers occur in a very specific pattern following 3 rules. The quantum numbers describe the electron, including the type of orbitals involved, as well as their energy level and specific locations and spin. S orbitals are filled with 2 electrons. P orbitals are filled with 6 electrons, D orbitals are filled with 10 electrons, and F orbitals are filled with 14. So this is kind of some review on quantum numbers, but electrons are going to be what we're going to be focusing on with electron configuration because it's a lot of what goes into why things react the way they do. So the 3 defining principles of our quantum numbers and our orbitals are the Aufbau Principle, and this principle describes how electrons are added to orbitals one at a time. So building up orbitals as we proceed from atom to atom, we do so by adding 1 electron at a time. So just like in an element, if we add 1 more proton, we become a new element. As we add 1 more proton, in order for that to be stable, we have to add 1 more electron. But they're only added 1 at a time, 1 orbital at a time. So 1 electron in 1 orbital at a time. Sorry, it's kind of a standard principle. It's hard to explain without just repeating yourself a lot. So that's the Aufbau Principle, adding things 1 at a time, or adding electrons 1 at a time. Then we have Hund's rule, and Hund's rule says that every orbital in a subshell will be occupied by 1 electron before any orbital is doubly occupied or spin paired. So all electrons in singly occupied orbitals will have the same spin before we add a second electron in an opposite spin. And you'll kind of see what that looks like in a little bit. But that's Hund's rule, is that every orbital must be occupied by 1 electron before any other orbital can be doubly occupied. And then the Pauli exclusionary principle, this is the rule that governs the fact that no 2 electrons can have the same 4 quantum numbers, and that's the whole idea of spin pairing and spin up and spin down. Any 2 electrons found in the same orbital must therefore be spin paired, so the 4th quantum number spin is not the same. Okay, so let's put it all together and see what that looks like. When determining what an element's electron configuration looks like, you need to take into account the Aufbau Principle, Hund's rule, and the Pauli exclusionary principle. And then begin filling the orbitals starting at the bottom with the 1s. So there's a very specific pattern in filling these orbitals, and that pattern goes not only by orbital type, S, P, D, and F, but also by energy level, 1, 2, 3, 4, 5, and so on. So the pattern for filling orbitals is dependent on the following model. And this is the best way that I have to represent it for you. And as you increase in energy level, you get to add a different type of orbital up until the 4th energy level, because we only have 4 types of orbitals. So when n is 1, you just have the 1s orbital. When n is 2, you have the 2s plus a new orbital called the 2p orbital. When n equals 3, you have the 3s, the 3p, and a new 3d orbital. And when n equals 4, you have the 4s, 4p, 4d, and 4f orbital, that new f orbital. And n equals 5 is 5s, 5p, 5d, and 5f, and so on and so on. Now the way that these get filled is a specific order, because it's not necessarily how you would think, because nothing ever is. But if you draw out this kind of triangle like this, if you draw an arrow down through each of them, you can see how it's filled. So you'll notice it goes 1s, 2s, 2p, 3s, 3p, 4s, then 3d, 4p, 5s, and so on and so on. So I'm going to show that. So you go from 1s to 2s to 2p to 3s to 3p to 4s to 3d to 4p to 5s to 4d to 5p to 6s. Okay, before you even reach the 4f. We probably won't be doing any f orbitals though, so I wouldn't worry too much about that, but that is as high as I normally go. So this is something that you're going to have to know the order of. So I would either write down the triangle or write down this order and start practicing that because you are going to use it. So there is a pattern with those electrons then. And that is following that same pattern, 6s, then 4f, and all that. And so an s orbital is going to have 2 electrons, a p orbital has 6, a d orbital has 10, and an f orbital has 14. Now, I like to I want to show you guys how you can fill it up by showing you the electrons filling in. And so when I do that, I like to start out with a 1s orbital and then a 2s orbital. And I like to go from the bottom and draw out the 3p orbitals, the 3 2p orbitals, a 3s, 3p orbitals, 4s. Then there's the 5 d orbitals in the 3d, then the 3 orbitals for a 4p, 5s, 4d, 5p, 6s, 4f. Okay? And so let's start filling in those electrons. So we're going to fill them one at a time. So the first one's going to go in 1s. Now, since there's no other orbitals in this energy level, the second electron that's going to go in is going to be spin paired and occupy the same orbital as that other electron. And so it's going to be spin down. Same goes in, so when we add our third electron, it's going to go into the 2s. The fourth will also go into the 2s. Now my fifth electron is going to go into my 2p. My sixth electron, however, is not going to be located in this same orbital. It's going to go in to another orbital, also spin up. And then my seventh will go in that final one, 8th, 9th, 10th. So you see how I went from each orbital has one electron in it, all spin up. Then I added another electron spin down. So that's following that rule about having to have them spin paired. And then we're going to fill 3s, 3p, 4s, 3d. So we're going to have 5 electrons all spin up, 1, 2, 3, 4, 5, before we can start spin pairing them, and they'll go spin down. And then 4p, then 5s, then 4d, then 5p, then 6s, then 4f. Okay? So those electrons are filled in one at a time in an energy level before being spin paired. Every orbital has to have one electron before you can spin pair them. Okay. So the periodic table can actually be broken up into orbital blocks so that you can kind of know ahead of time what an element's electron configuration is going to be and kind of what electrons they have and where they should be. So this side of my periodic table is my S block, including helium. Then I have my P block over here, the D block in my transition metals, and my lanthanides and actinides are my F block. So electrons that get filled in these first two columns of the periodic table are all S orbital electrons. The electrons that go into these 6 are all P electrons. These are all D, and these are all F. Now the interesting thing that helps me is that if you look, the S block, which an S orbital only holds 2 electrons, an S block is 2 columns wide. 1 electron, 2 electron. The P block, which has 3 orbitals, which can each contain 2 electrons for a total of 6 electrons, is 1, 2, 3, 4, 5, 6 columns wide. F block, you can guess it's going to be 14, and the D block is 10. So each column represents the addition of 1 new electron, just like each column represents the addition of 1 new proton to make it the new element. So you can kind of go with that idea when we're talking about electron configuration. So, periodic table can further be explained by adding the multipliers to determine which quantum number is going to be used for which orbital group. So if you look at your periodic table again, the n value is which row you're in, or which period we call them. 1, 2, 3, 4, 5, 6, or 7. S orbitals, whatever n level you're in, that's the S multiplier. Same with P. Whatever n level you're in, that's your P multiplier. D multipliers are actually n minus 1, and F is n minus 2. So, sorry, I forgot I put that in there. Okay? So what that means, if I had my first, second, and third and fourth periods, if I'm looking into my third period, I have the 3s, and then I go over and I have my 3p. Now, if n equals 4, I have 4s, but now in the D block in that area, it's n minus 1, so n is 4, so this is actually my 3d followed by my 4p. And this can help explain the fact that the 3d doesn't get filled until after the 4s has been filled and what order it's going in. So it helps to kind of explain that. Okay, so let's talk about filling 3d and 4s orbitals. Special circumstances occur when attempting to fill 3d and 4s orbitals, which explains why the 4s orbital is filled prior to the 3d orbital. So if we look, so we've got each energy level is given a different color. 1 is blue, 2 is red, 3 is green, 4 is yellow. And this is an increasing energy. Now as I go up, you can see that it requires more and more energy the higher up your energy level goes to put those electrons in. And so you're going to want to fill from the lowest energy level. If you're going to have to fling an electron into that, or not fling, but if you're going to have to put an electron into one of these orbitals, you're going to want to expend as little energy as possible, which is why 1s is filled first, then 2s, then 2p, then 3s, then 3p. Now if you look over here, the 3d has a slightly higher energy level than the 4s, or energy, than the 4s, which is why 4s is filled before 3d, followed by 4p. Okay? The trick comes when looking at the arrangements, and there should be 9 electrons in the 3d orbital. There's a better way to have uniformity, and so the 4s gives up an electron to have a completed orbital in the 3d. Okay. This also occurs when there should be 4 or 9 electrons in the 3d orbital. There's a better way to have symmetry with 1 or 2 electrons in each of the 5 3d orbitals so that the 4s gives up an electron. So I'm going to talk about this in a second, but essentially, because there's such a small difference in the energy level between 4s and 3d, sometimes the symmetry of having a full 3d orbital or a partially filled 3d orbital outweighs the energy cost of getting it into a 3d from a 4s, and so the 4s will sometimes donate. So let's look at that. So copper has 29 electrons versus nickel, which only has 28. So if I fill in their electrons, I'm going to count out my electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay? There's my 29th orbital. Now you'll notice I am only 1 electron away from having a full 3d orbital, which would be very, very stable. So because of that, the copper will sacrifice an electron from the 4s and actually donate it to the 3d orbital to create a full shell because it's so much more stable. So that electron in the 4s will be taken out of the 4s and actually put up into the 3d. Now if you look at nickel that only has 28, so if I fill in all 28, I'm 2 electrons away. It's not going to want to donate both of those electrons from the 4s, so it will stay with this less stable configuration because the energy cost to donate is not worth it. So the key here is that the energy cost and gains that create the most stable atoms. So you're looking for the energy gain of creating stability versus the cost of donating it up. And here, it just costs too much to donate 2 electrons, and so this instability is more favored than the stability of a full d orbital. Same thing goes with chromium. In this case, chromium, so I'm going to fill in my electrons. Chromium has 24, which means I'm 1 away from a partially filled orbital, which is considered, if you had a filled or a partially filled or 3d orbital, that would be considered more stable. So that 4s again is going to sacrifice an electron to put it up into 3d. Vanadium, on the other hand, again, this is 2 electrons away. The cost is too great, and so it stays as it is. Okay, so let's talk about electron configuration. And let's have you guys find some electron configurations, because that's what we've been doing. So what is the electron configuration of magnesium? So if I look, I can lay out my 1s, my 2s, my 2p, and my 3s. And I'm going to fill in. Magnesium is atomic number 12, which means it has 12 protons and 12 electrons. So I have 12 electrons to find homes for. So if I add them, I get 12 electrons. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be my my full electron configuration. That's where all the electrons go. So if I wanted to write it out, I would say 1s2, 2s2, because I have 2 electrons in the 2s orbital, 2p, and I have 2, 4, 6 electrons, and then 3s2. But what about oxygen? So I want you guys to do this one yourself. Fill in those oxygen orbitals with electrons. Oxygen, you should be able to find that on your periodic table, and then come back with an electron configuration. So go ahead and pause it, fill in your electrons, and then write an electron configuration, and then come back and check. So oxygen has an atomic number of 8, so it should have 8 electrons in its orbitals, which if you fill that in, you get 1, 2, 3, 4, 5, 6, 7, 8. So my 1s orbital has 2 electrons, my 2s orbital has 2 electrons, and then my 2p orbital now only has 1, 2, 3, 4 electrons. So that is my electron configuration for oxygen. Alright, so I want you guys now to find the electron configuration of arsenic, and then check in with me. Okay, so arsenic has, oh, I can't see it, it's got a glare. Arsenic has 33 electrons to take care of. So those all fill in like that. Those are only 33 electrons. And so if I write out its electron configuration, I get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p3. What about silicon? Go ahead and take a pause and find silicon. So silicon has an atomic number of 14, which means there's 14 electrons to take care of. So filling those all in looks like that. And to write the electron configuration, I would say it has a 1s2, 2s2, 2p6, 3s2, and a 3p2. So we're going to do a lot of practice with this, and this is also going to help you with practicing your atomic element symbols for the mastery quiz that's coming up. So have a good night, and I will see you tomorrow when we practice this.